close this. All right. Now we apply the lambda f dot ff to the a, and we remove the head, and we have lambda f dot fa. Well, no. Instead of f, we're going to have lambda f dot ff. It's just really messy like this. And I think it's like this, right? Lambda f dot ff. I don't know. But now we have to apply lambda f dot ff to the, and remove that head. So we're going to have lambda f dot ff and lambda f dot ff. Okay, we got the same result. The self-apply being applied to the self-apply. Omega combinator. I really like this, how slowly and slowly and slowly we are coming to the recursion by doing recursion all the time. But it's like usually the recursion is shown like here's the base case and here's how you do recursion. But so far we have seen so many examples of non-terminating types of recursion. So I guess when the terminating type comes, we'll have much more appreciation for it. And appreciation, helps with intelligence and learning. It really helps when you appreciate something. It's very helpful. Wow. What a nice thing. You can make a screenshot. Maybe like this, maybe like really big. Can I do one more? Okay. Could do a screenshot like this. Yeah. Would be nice. Maybe put some kind of a sticker here. What kind of an image would a self-apply being applied to self-apply? Yeah. This is nice. This is nice. Very happy about this. And it's nice how Greg also introduces all of these things without explaining them. I mean, he explains them, but he doesn't. That's a very pedagogical style. Like he shows you something, he explains it to you, but he doesn't really give it a name. Or he lets you, like he showed you the self-apply. He called it self-apply, and he didn't call this. Welcome to chat room. Did the stream stop? But he doesn't, 0 viewers. Oh, I had a viewer then. Session 358. It did stop. Oh. There was a network error. It stops every single time. Weird. I really like this approach. So it's the self-apply and self-apply, and it's so hidden here. Omega combinator. This here, Omega combinator. So let's do the fourth one. Let's do the fourth one. So now we have a lambda p, lambda q, pq being applied to lambda x dot x, lambda a dot lambda b dot a. And outside of that is lambda q dot q, again an identity function, only with lambda k dot k. So we have pq, pq. So actually we have here the apply function. This is the apply function. This is the identity function being applied to the select first function. Like he's making all of these little combinations, and outside there is an identity function. So what could we do? Well, we could substitute, I guess, the identity with the p and the select first with a q, right? We could do that, which will leave us with just pq, right? P is this and q is this. So we basically can just remove this. We can just end up with this, and this being applied to this, right? But actually, if lambda x dot x is being applied to this, well, this is just the identity. It returns the thing. So we just have lambda a dot lambda b dot a being applied to lambda k dot k. Hey yo, and lambda k being applied to lambda a, we substitute for the a, so we get a lambda b dot lambda k dot k. Yeah, we just get a lambda b dot lambda k dot k, and that's it. Fascinating. Let's see what ChatGPT will do with this one. Will we get the same result? Hello. Welcome to Lambda Calculus, the amazing, fascinating Lambda Calculus. Isn't it cool? Do you also like Lambda Calculus? Let's evaluate the expression. Right, the outer application. I hate lambda. Oh, why do you hate lambda? It's like the machine code of, computation. Functional. Well, if you look at functions, it's the machine code. It's so beautiful. It hurts my head. Yeah, of course. No, it hurts the head. But you know what's nice? That you understand some of the concepts and you see how they move. Right? It's incredible. I don't know how long you've been here, but it's like this thing, what we did, look at this thing. Of course, it hurts your head, right? And I've been doing this for like a couple of weeks, so now it does not hurt so much. But do you see this? Lambda f dot ff being applied to lambda f dot ff. This is just a function that applies something to itself. So this is the self-apply function. This basically never stops. This is just a loop. This is like a loop being applied to a loop. But the thing is, these are just functions. They have no values. Like, it's not like you could say, but what is it looping, right? No, it's just the idea of a loop. Can you believe, like, the idea of a loop being applied to the idea of a loop? What do you get? Well, you get the idea of a loop, right? It never stops. But what we have here now is in the idea of a loop, right? You're applying some kind of thing in the idea of a loop. But here the whole idea of a loop is being applied to the whole idea of a loop. So it never stops. But this is kind of the beginning of understanding recursion, because then these things will be expanded a bit and there will be a way to stop it, to stop it until some kind of a base case. And that's kind of cool. Or like the AFFA here. This is the apply function. Yeah, I've been doing this now for 2 weeks, I think, and it's fascinating. Today we did the make pair, or like the select first. A make pair that like makes a pair from two things. And I was so surprised. I was saying that in the previous video. I was so surprised. I almost had the idea that make pair. And look at this. This looks simple. Okay, look, you have a lambda A. Yeah, I'm in a college level math, like, but it's like, it makes sense, but it's just so annoying to do. Yeah, it's annoying to do. But have you heard about the church pairs? Like, I thought college level math. Oh, you do calculus. I thought like this pair thing, it's going to create a pair, but it doesn't create a pair. Like A, B, and F, and then some kind of a function that does something to two things. It does not create a pair. It just tells you, okay, with some kind of a function that you give me, I will do something to these two things. And you're like saying, well, give me two pairs. Well, what do you want me to do with the two things? What two things? You know, it's like, it's just so subtle. It's not so concrete as we are used to, like make pair and you get some kind of a structure. But yeah, anyway, I know it's hard. It's not really for the, you know, but it kind of, in an indirect way, when you do this, then some other things I get, okay, I don't know. Yeah. College level math. Well, I like discrete mathematics. Well, this is discrete, right? Because these are actually, so far, more than continuous. But this is discrete. You know what? I think this is discrete because we are talking about combinators. Isn't this weird? Like, even when you look at something like this, look at this, lambda k dot k. Lambda k dot k is a combinator, right? Isn't this, does that belong in discrete mathematics because it's a combinator, right? This, I don't think this is not continuous. But you probably know this better than me, you know. Because it does not have any, lambda is discrete. Yeah, okay. And this book is nice that I'm going through because he's not just showing in the books. I really couldn't understand some of the books. He starts really slow. Like, maybe this sounds like, you know, but this is now not so hard. And he starts really slow from the beginning of the book. I like stuff like graph and number theory stuff. Oh, cool. He really does. He uses the Lambda Calculus to really program with it, not just to show. In a lot of the books, I mean, the tutorials I show, they just show, you know, you have a term, you have abstraction, you have this, blah, blah, and then some rules, and then some proofs or something, and I don't get that, you know. But here he's kind of playing with it a lot. And like in here he actually showed here the omega combinator, and he didn't name it. But it's kind of, you do things, you know, like when you do things and then after a while, oh, that's what I was doing. Wow. So yeah. So did we solve this lambda b dot lambda k dot k? Lambda b dot lambda k dot k. Yeah, it's true. Final result lambda p lambda k dot k. This is a curried function that takes two arguments, ignores the second, and always returns the identity function. So this is like a Boolean, yeah. Like a true or false. Okay. What did we solve now? this thing, this thing. Okay, now we have this one. This one is a big mess. Okay, just this one now. Wait, let me do it like this. Lambda f, lambda f, lambda g, lambda x. So I have 3 scopes, and inside of it we have a bound f, bound g, bound x. Oh, okay, so we have actually a make pair function here. This is a make pair function right here. And lambda s.ss, this is the self-application function that never terminates. Outside of that, on the level of the lambda x, actually, lambda x being applied to this, yeah, we have a lambda a, lambda b, lambda b. This is the select second function and select first function. Okay, we have select second, select first, self-apply here, and make pair function. So I guess we're going to substitute now the lambda ff with the self-apply function. So the self-apply would be lambda s.ss, and then we, oh, I'm again doing the same mistake. We remove the head. So I get lambda g dot, lambda x dot, and instead of the f, I put the self-apply function, lambda s dot ss, and outside of that gx. And then I have lambda a dot, lambda b dot b, lambda x dot, lambda y dot x. Could put it here like this maybe. So now we have lambda g, lambda x, this thing being applied, and lambda a, lambda b, lambda b. So now we're going to apply the select first function. Well, we're going to substitute it now for the g. So we remove the g head, lambda x dot, lambda s dot ss, and g. Well, g is going to be now our lambda a that we took, lambda b, b, x. And outside of that, lambda x dot, lambda y, x. Wouldn't it just be lambda s dot ss? What do you mean? Oh, we substituted the lambda s dot ss for the f, right? Yeah, look at this. The lambda s, we substituted for the f, and we removed the f head. So that leaves us with lambda g, lambda x, and then the ss is here, and the gx, right? And then the rest of this thing. Now we go to the next one. We have this one. We substitute it for the g and remove the g head. We have now lambda x, lambda s dot ss, and now lambda a dot, lambda x, and now we have this thing. So look, and now we have this thing, and we're going to substitute it for the x thing, and this is the select. Look at this. This is actually the select first. So it takes the first, then it takes the second. It doesn't take the second, and it gives back the first. So this whole thing now we're going to substitute for the lambda x. So we remove the head, and we're going to stay with lambda s dot ss, and we're going to have now lambda a. We just copy this, lambda b dot b, and x, and instead of the x we put now lambda x, lambda y dot x. Maybe I don't need that many levels of these guys, but I don't know. And now we have lambda s dot ss being applied being applied to this expression. Lambda a dot b. Wait a second. Here we have the select second. We have a function that gives back the second argument, and we have here this function that gives back the first argument. And we have to, oh shit, we're gonna apply, oh shit, we're gonna apply that, we're gonna substitute that here in SS. Well, we're gonna have a mess now, because this is the self-apply function. It never stops. So if we substitute, it's just curious, or maybe we substitute. Yeah, maybe I should have been more careful with the parentheses. One option is that this whole thing, this thing, goes inside of the S. So this thing will just be applied to itself. Or maybe we could simplify this, actually. Could we simplify this? Look at this, A, B, B. So actually, yes, if we do this function and substitute it for the A, well, there is no A here, so it's going to get dropped. So we're just going to have lambda b dot b. And since lambda b dot b is the identity function, we're just going to get lambda s dot ss. That's one option. We could just get lambda s dot ss. Yes. Even if we now took the entire thing and substituted it here, and being applied to itself, we can still simplify it. So this thing goes inside of this thing, A drops it. There's no A here, so we're just gonna left with B. So the solution would be lambda b dot b. And here we have lambda s dot ss. And the solution is the identity, which just gives us, this is the end. And then sub back, simplify more. Well, you also got the same thing. I just don't understand. What did you do here in the end? Then lambda x. What do you mean lambda x? I thought this is the end, right? Lambda b dot b. I think that's the end. Let's check here. ChatGPT is good with these lambdas. So far, he's been proven really right. Substitute SSS for F. Right. That's what we did. Lambda G, lambda X. Right. Simplify. Yeah. Lambda B, lambda X. Wait a second. I forgot the lambda X. Lambda BB. No, look at this. It's the same thing. Lambda X. Oh, I forgot something actually. Yes, you got the right thing. I forgot something. X. Oh, I forgot the X. Look at this. No, I didn't forget the X. I thought I actually substituted this. I made a mistake. Lambda X. Yeah, I thought we were going to drop this X head. And no, I did a mistake here actually. There was something wrong I did here. This is not correct. You did this right, yeah. Substitute in X lambda A dot lambda BB X. Simplify. Yeah, that's correct. I made it. What did I do wrong here, actually? Right? I thought like you substitute. Oh, look at this. Something I did something very bad. Evaluate the first application. Substitute lambda s.ss for f. Yeah, that's what we did. You get the gx lambda s.ss gx. Apply gx to lambda a dot lambda b dot b. Right. And I get lambda x. Yes, lambda s dot ss lambda a dot lambda b dot b x. X. Right. That's what I did. Step 3, simplify lambda a lambda b x. Simplify this. Oh, he's applying this x to get. Oh, what happened with this one? It's like this is dropped. He's simplifying this x and dropping it, then you got lambda b dot b. That's what I did wrong. Now the expression becomes lambda x dot lambda b dot b. Lambda b dot b, simplify. And now he's simplifying this. It's fun. It's like, what happened with lambda x? Yeah, I don't get it. What happened with this thing here? Lambda x dot. Why is this not shown here? This thing. Yeah. Somehow gone. Erased. Substitute. Yeah, you're right. It does hurt your head a bit. It does hurt your head. I'll have to return to this. This also hurt my head now. This really hurts my head now. Yeah, I think it's good to make a break. Lambda x. Well, that's our last one, actually. For each of the following pairs, show that function a is equivalent to the function resulting from expression by applying both to arbitrary arguments. For each of the following pairs, show that function a is equivalent to the function resulting from expression b by applying both to arbitrary arguments. Oh, so we have to show that they are equivalent. What kind of equivalence is that? I also wonder. Like lately I learned about extensional and intensional equivalence. Identity, apply, identity. Yes, well this will be the same, but it wants us to apply an argument. For each of the following pairs, define a function, then define a triplet. We had to make pair. Identity. Well, if we apply identity to argument, wait, I still can't really. I'll just ask, what happened with this thing? Wait, I can check that like that with ChatGPT. Wait, I don't get it. What happened with this thing in the expression? Overlook the final application. What? He's now correcting himself step by step. Final result. No. This is, yeah. Yeah. The lambda f. Okay, let's try that next thing. Identity. Well, identity to argument just gives back the argument. Identity. When apply identity argument. Could show it with apply, I guess. Apply identity. And that would be the same actually. Even if we show it in GCI. Do I have apply? Wait, type apply. I have it defined. Type identity. I don't have identity. Now I have. Okay, so identity 2 is same as apply identity 2. No, it cannot compare them like this. Yeah, like this. It's true. They're the same. But if we apply it to some R, to some A, that's lambda F, lambda A, FA, and also lambda F dot lambda A dot FA being applied to lambda X dot X outside of that to A. So yeah, I'm substituting for the F and I get a lambda A dot, and instead of F I get lambda F dot FA, A inside, and lambda X dot X, A. I could substitute lambda X dot X with the A. I'm going to get lambda F dot FA and lambda X dot X and A. Wait. Maybe I'm again actually rushing. Wait, how did I get apply. Lambda A. FFA. Yeah, that's correct. And then A. And now I could substitute the identity with the F. And then I get lambda X dot X, A, and then A, which just gives us A. Yeah. I think I have to make a pause now. I've been doing this for a while. Yeah, I'll just make a pause now because it's been, as you said, head hurts a bit. Yeah, but it's good to make pauses and breaks, you know, it's important. So yeah, also thanks for dropping by. All best. I'm gonna stop now actually. Okay. Bye.